There we are. All right, welcome. Thank you. Thank you. How was Bozeman?
That's all right.
Good. Yeah, good weather, or was the path pretty treacherous?
I think it was good. I was thinking mine was something.
Well, that's good. I live here for Montana. All right, so what's the official world record for the G-forces? 46.2, right? So what does that mean exactly? 46.2 Gs. For an instant in time, he felt like he weighed 46.2 times his body weight, right? So that creates problems, especially for the heart to circulate blood, especially for blood to get from the lower extremities back to the heart. So alternatively, from the article, why is 1 G that we experience under normal circumstances, why is that a good thing?
Your body doesn't fall apart.
Yes, yeah. So we have bones that need to maintain their density. We have muscles that need to maintain their mass. We have cells that need to maintain their integrity. So it is a good thing. So to avoid osteoporosis, the recommendation is weight-bearing activity, right? So forces that are equal to our body weight or even in excess of our body weight, but within controlled conditions. So some people over time can tolerate greater impact than other people, but you have to build up to it. So it's not something that someone that's been doing a lot of impact type exercise would be different than someone that is just starting an exercise program. So how do we define the force of gravity then? It's a force that acts on our mass, right? Mass is substance. Mass takes up space. So what does the acceleration do to gravity? Those that had lab today will know. Yeah, so it's negative 9.81 meters per second squared. So that's an ever-present acceleration. So why is it that we don't just fall down then, if we're under this ever-present acceleration? Yeah, because we have the ground that holds us in place, right? So it's the universal law of gravitation between the Earth and our body mass. And so that's very important because, as you'll find out in lab this week, we can calculate different things, jump height and so on, from gravitational acceleration. So how do you define friction then? So if we're talking about a normal contact force, if we have a normal contact force, we can divide it into two components. The parallel component is friction, right? Okay. The perpendicular component is the normal reactive force. So there's two parts. So the way that we apply force into the ground determines the exact reactive force. So friction is the parallel component of the reactive force, whereas the normal contact force is the perpendicular component of the reactive force. So how do we calculate friction then? So we need to know two things. One is unitless, right? So that's the coefficient. And typically, under normal circumstances, how high does the coefficient go? From 0 all the way to 1, right? So it's a unitless number, and so a higher coefficient of friction means that we have either a rougher surface or greater resistance to sliding. So what's the other component of calculating friction? And the coefficient of friction multiplied by, sometimes if we're on level ground, it can be equal to our weight, multiplied by the normal contact force. So if we are on level ground, the normal contact force is going to be perpendicular and equal to our weight. We can also be, as was the case with some of our practice problems, squeezing a tennis racket. Okay, so we're not in contact with the ground, so the normal contact force would be provided by our grip force on the racket. So my goal for today is to continue on. We're going to talk about resolution of forces today. So if we have multiple forces acting on a body or object, how do we come up with just one force? So we have to know how much force, but what other factor do we want to know if we're talking about force? Especially because force is a vector. So if we have force, we want to know how much, but what else? Direction. Yeah, direction. So oftentimes direction is described by an angle. So we'll learn how to calculate the force, the overall force, then also the angle of application. So question for you, if I were to drop a bullet from this height and I were to shoot a bullet from the same height, which one would hit the ground first? Ignoring air resistance. They would hit the ground at the same time. Why would you say that?
Because the horizontal component doesn't matter.
Yes. The horizontal component doesn't matter with gravity. So gravity only acts what direction? Vertically. So although the bullet that we shot from a gun would have a horizontal component, what's it doing as it travels horizontally? It's also dropping. At what rate? What is the acceleration of that bullet as it drops towards the earth? What's the number? Yeah, negative 9.81 meters per second squared. So that's the rate of change in velocity. So the bullet that I drop from that same height would also be accelerating towards the ground at the same rate. So they would hit the ground at the same time. So there was actually, how many remember the show Mythbusters? A few years ago. They actually did this experiment, so it's a 2-minute video I'd like to show you so you can actually see that this is actually true. So we'll go ahead and take a look at this first. I don't think we could approve this to try this in a biomechanics lab. But it would be fun.
Everything's hot, let's do it. And after a few test fires and a bit of fine tuning, it works. 14. Oh, it's good. It's good. It's 1/3 of a millisecond difference. Wow. That's freaking perfect. Let's go do this full scale.
Okay.
Which means rolling up the room 360 feet to stake out a drop zone. Right about there. That's where they were landing out in the shooting range, so this is where I expect them to land here. Okay. Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig. So the boys can take a shot at physics history. All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed. Let's go see where it hit. So Adam takes a one-wheeled ride down the room to check out the drop zone. Wow. And the results are simply ripping. Can't get much closer than that. I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for. In real time, it's impossible to tell what happened. Until Adam analyzes the high speed and crunches the numbers. 3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves. And a victory for physics. Feel this.
Kind of neat that somebody decided to test that. Okay. All right, so the second half of this chapter, resolution of forces. So first thing we're going to talk about is force composition. So we have two different types of forces. The first one is collinear, the second one is concurrent. So collinear forces are pretty easy to resolve to determine the resultant because the forces are acting along the same line, so although in opposite directions. So this makes me think of, I was a professor in Illinois for about 11 years, and during Greek week, one of the competitions between different houses was a tug-of-war. And what made this tug-of-war even more interesting was there were two teams, each positioned on either side of a lake, big lake. So it was fun to watch because you'd have these people pulling in opposite directions to the point of exhaustion, and guess what happened with the loser? It was far enough to where the loser would end up in the lake at the end. So Greek week, crazy. But that's a perfect example of collinear forces. Forces that are acting along the same line, so in this case the rope, but in opposite directions. So let's take an example. So let me, what I can do to save you paper is you can just write these on your practice problems from last time. And then you'll have to get a new piece of paper every time. Haley. Everybody seen Brian today? Must be out running. All right, so you can just continue on. So, one of the best female weightlifters in the world, Lydia Valentin from Germany. So in this case, attempting to jerk a 147 kilogram barbell. So 147 kilograms represents what? What variable is that represented in kilograms? Mass. Yes, so mass is not a vector quantity, it's scalar. So we want to know how much, but we don't have to define direction. So 147 kilogram barbell, she exerts a 1700 Newton upward force. So that's the force that her hands are applying to the barbell. What is the net vertical force exerted on the barbell? What is the instantaneous vertical acceleration of the barbell? Okay. So we're asked two questions here. The first one is the net force. So if you look at the barbell, you have this athlete applying an upward force, but what other force do we have acting? Gravity. That's always the answer, most of the time. Okay, so how do I determine how much 147 kilograms weighs in newtons? Yes. So what's the value again? Yes, negative 9.81 meters per second squared. So if you multiply 147 kilograms by negative 9.81 meters per second squared, what do you come up with? Let's go with two significant digits today. So 1700 newtons up. That's the force of the athlete on the barbell, but Gravity also is acting on the barbell in the opposite direction. So you're going to have a net force. In order for that barbell to go up, there has to be a net force. So if the weight and the net force are equal, where's the barbell going to go? It's going to go anywhere, right? So the net force has to be positive in order for the barbell to go up. So what'd you get in newtons? What's the weight of the barbell in newtons? 1,004 something?
Yeah.
1,400, what's the exact number?
42.
1,400?
42.
42, that's a negative number. So again, let's go with two significant digits. What were they? 0.07. Okay, so you simply put those two together. So you have a net force of 1,700 minus 1,442.07. So what's your net force? It's kind of like your checking account. You got your deposits and your withdrawals, and hopefully you don't come out in the red. In this case, it's good because the net force is positive. So it's probably going to be something like 200 something. Positive, what is it? Yes, 257 newtons is our net force. So we can calculate instantaneous acceleration. So what does that instantaneous word mean? So all throughout this course, we will look at instantaneous values, we'll look at average values. What's the difference between an instantaneous value versus an average value? So instantaneous means it happens in an instant. So at the moment that net force is applied to the barbell, there's going to be an acceleration. So what's the relationship between, mathematically then, if the net force is equal to mass times acceleration, what's the relationship between the net force and acceleration with a constant mass? The greater the, if mass is constant, the greater the net force, the greater the acceleration. So it's a proportional relationship, right? Okay. So the greater the upward force you can generate against a constant mass, the greater the net force is going to be, and the greater the acceleration of the barbell. So then if we take this equation, so Brian, you said 257? Okay, so 257 newtons equals our mass of 147 kilograms multiplied by the instantaneous acceleration. So how do we solve for acceleration? Easy, just simple algebra. We divide the net force by the mass, right? What are our units for acceleration? Yes, meters per second squared. Linear acceleration, meters per second squared. So you should have something like 1 point, it's going to be over 1.5 probably. So 257 point something divided by 147 kilograms. What did you get for your acceleration? 1.75 meters per second squared is the positive acceleration. Okay, so are there any questions on collinear forces? So this is an example of collinear because the weight and the upward force from the athlete are along the same line, but not necessarily in the same direction. So that's collinear. Okay, all right, so let's move on to concurrent. Okay, so concurrent forces act through the same point, but not necessarily along the same line. So usually that point is a person's center of gravity. How many have heard that term before, center of gravity or center of mass in relation to objects or bodies? So what do you think of when you think of center of gravity or center of mass? we use those terms, they mean the same thing for the purpose of this class. Center of gravity or center of mass.
Middle of your body, kind of.
Middle, yes. Or maybe we could say a balance point. So center of gravity or center of mass is defined as the point around which the mass of the body is equally balanced or distributed. So to make things simple, because your body has segments that are connected by joints, we say the body has one overall center of gravity or center of mass. And so we're talking about forces that are applied through that single overall point. So multiple forces that are acting along different lines through that single overall point. So a practical example here, how many have seen, maybe watching the Olympics? So there was a really good meet yesterday between Utah and Oklahoma. How many saw that or watched it? Two of the top gymnastics programs in the country. But at any rate, an athlete jumps up, and then the coach is usually there for a brief time just to kind of steady their body before they start the routine. So that's what we're talking about here. So a gymnast is about to begin his routine on the rings. He jumps up, grasps the rings, and his coach stops his swinging by exerting forces on the front and back of his torso. What is the resultant force acting on the gymnast? Okay, so if we make a free body diagram, and remember the length of the arrow represents what? So we're drawing force vectors we're representing force vectors with arrows. So the length of the arrow represents how much force we have. And so the athlete jumps up, grabs the rings, and there's a force of 550 newtons. So the athlete applies a downward force on the rings apply a reactive force back on the athlete's hands, and so 550 newtons in the upward direction. Okay, so we also have weight, and in this case, weight is equal to 500. Is that negative or positive? Should be negative, right? So we have two vertical forces in opposite directions. Okay, so these two forces are collinear, but we also have the forces from the spotter there. So we have one force of 20 newtons acting in this direction to the right. We have another force of 30 newtons acting in the opposite direction to the left. So what we want to come up with is one overall force, because that determines the outcome. So when you look at all the forces acting on an athlete's body, what's the one overall force? And what's the angle? So we can take this free body diagram and we can make a triangle out of it. So what kind of triangles are these? From way back, maybe in high school, probably. Right triangles. So okay, so right triangles. So all of these are right triangles of different sizes, but the angles within each of these particular right triangles are exactly the same, and they add up to 180 degrees. So if we were to add all three angles, you have one that's equal to 90 degrees, so the sum of the other two is also equal to 90 degrees. So they all add up to 180. Okay, so right triangles are special in that you have these trigonometric ratios. So these ratios of the sides of a right triangle relative to the angle. So we're talking about the angle theta. So this is the angle, not the 90-degree angle, but the other angle here. And so here's those ratios. Do you remember from high school? So maybe you can kind of get that memory back out, brush it off. But we've got these ratios of sides. So sine theta is equal to opposite over hypotenuse. So the opposite side is defined as the side opposite the angle theta. So here's a right triangle. And if we say this is the angle theta right here, then the side opposite the angle theta. So that's the opposite side. The adjacent side is next to the angle theta. That's what adjacent means, is next to. And then the side opposite the 90-degree angle here is called the hypotenuse. So is it starting to come back? Yeah? Okay, well this is as far as we go into trigonometry, so, but we try to make it practical. So we'll go over some examples. If we want to calculate the angle, we can do that too. So we take the inverse trigonometric function. So if you look on your calculator, first thing you want is to make sure your calculator is in degrees rather than radians. And just from looking around, it looks like we have lots of different calculators. So don't be discouraged if you put in something and you don't quite get the right answer. From past experience, sometimes there's a little bit of a learning curve in reviewing how to put in these numbers. So you have the regular trigonometric functions here, sine, cosine, and tangent, but what do you see just above those keys? You should see these inverse functions. So we use those inverse functions if we're calculating the angle theta. And that's important. We want to know how much the resultant force is, so the magnitude, but we also want to know what the angle of the resultant force is. So if we know two of the legs other than the hypotenuse, we can calculate the hypotenuse using Pythagorean theorem. So you've all done this several times before. So a squared plus b squared equals c squared. If we know one of the legs, any three of those legs, so hypotenuse, opposite, or adjacent, if we know one of those plus the angle theta, then we can also calculate the magnitude of the other two sides. So we'll go through a few examples of each of those. Okay, so getting back to our problem, we need to come up with an overall net force horizontally and an overall net force vertically. Okay, so remember first day of class we defined as positive what two types of forces? Positive is up and to the right. Typically it's done that way. So negative is down and to the left. So let's stick with that. And so what's our net horizontal force then? So we have 20 newtons to the right, 30 newtons to the left. What's our net? 10 to the left. Or we could say 10 left is negative 10 newtons, right? Okay, so that's our net force from the horizontal direction. Did everybody see how we got that? Okay, so what's our net force in the vertical direction then? Yeah, 50. So you have 550 newtons in the upward direction, the reactive force from the bar on the hands, and then we have 500 newtons from the athlete's weight. So the net force in the vertical direction is positive 50. So now we have a 10 Newton net force horizontally, so we say to the left, and we have a 50 Newton force vertically, right? So we can make a right triangle out of that.
So we don't put the negative, we just do it as.
You could just point it to the, means the same thing, yeah. So, and even with the Pythagorean theorem, you'd still get positive. So, okay, so I want you to tell me, how do we come up with 51 newtons as a resultant? So can you use the Pythagorean theorem to get 51? So a squared plus b squared equals c squared, or in other words, c, which is your resultant, is equal to the square root of what? Let's go to our board here. Okay. So we can also write this another way because we want to solve for the hypotenuse. So we can also say that C by itself is equal to the square root of a squared plus b squared. Okay, so it really doesn't matter what side you choose to be A and what you choose to be B. I traditionally like to say the opposite side is A, the adjacent side is B. So if you work this out, so if we have 50 squared is equal to 2,500, right? 10 squared is equal to 100. So you have pretty much what you come up with is the square root of 2,600 newtons. Okay, so then taking that, you should come up with something pretty close to 51, maybe like 50.99-ish. So 51 newtons. Okay, so we have all three sides, so we can use any of our inverse functions to get the angle, right? So say we were to use the inverse tangent function. So theta is equal to the inverse tangent function. What's my opposite side for that right triangle? Remember?
10.
Let's go back and take a look just to make sure. Okay. So this is going to be our angle theta right here. So the reason this is the angle theta is because we want to know the angle of this resultant force acting up and slightly to the left. Okay, so if this is theta right here, this side over here is going to be what? Opposite. This side right here is going to be what? Adjacent, right? And then so we've already solved for the hypotenuse. So if this is the angle theta, the angle relative to the horizontal that our resultant force is acting, we can use the inverse tangent function, opposite over adjacent, multiplied by the inverse tangent function to get the angle. So this angle is pretty steep, isn't it? Is it greater than 45? Yeah, 45 is kind of right in the middle. So it's going up. It's not 90 though, right? 90 would be straight up, so it's a little less than that. So let's take a look. So we have our opposite side, which is 50, divided by our adjacent side, because tangent is opposite over adjacent, right? So usually on the calculator, you'll have to use the shift key to access those inverse functions. So you should come up with something around 80 degrees, maybe a little less than that. Yeah, 79, roughly 79 degrees. So pretty steep, 78 point something. Okay. So we're rounding up, so right around 79 degrees, or exactly a little less than that. Okay, so we have the magnitude of our resultant. We also have the angle, so that would complete that analysis. Okay, so questions so far? Comfortable? Okay, all right, let's look at something else here. Okay. Bryn, right? Yeah. Okay, so at the instant shown below, 100 Newton force is applied to a 4 kilogram shot at an angle of 60 degrees above the horizontal. What is the net force acting on the shot? Okay, so let's set this up. 4 kilograms. How much does 4 kilograms weigh in newtons? How would I figure that out?
Multiply by.
Yeah, you got to multiply by that. Negative 9.81 meters per second squared. 4 kilograms So you're going to end up with something just under negative 40 newtons. 39 something, what is it, Ashley?
39.24.
Yeah, okay. So that's vertical, right? It's in the negative direction, but it's in the vertical plane versus horizontal plane. Okay, so now we have this 100 Newton force that is also acting on the shot. So you have two different forces acting on the shot. You have force of gravity acting on the mass of the shot, but you also have the force from the athlete. So what we want to know is what component of that 100 Newton force is horizontal and what component is vertical. So how can I tell that there's both horizontal and vertical components just from reading that? How can you tell that there's a component that is pushing that shot out and a component that's pushing that shot up from this overall resultant? So in this case, the resultant, or we could say the hypotenuse, is given to you, right? So your objective is to figure out what component of this resultant is vertical and which component is horizontal. So both of those numbers are going to be positive. So let's do this together. If you go to the next slide there, we can represent this graphically like this. Okay, so a 100 Newton force from the athlete on the shot. Okay, so what was the angle here again? In other words, what is theta? Yeah, it's 60 degrees. Okay, so that's what's represented there. There's your right angle. So you have two different components to this 100 Newton force. You have horizontal, so that's the part that's pushing the shot out, but you also have a vertical part that's pushing the shot up. And because the angle is greater than 60, what can we say about how the horizontal and vertical forces compare? Which one is greater because the angle is greater than 60? The vertical will be greater. Okay, if the angle was less than 45 degrees, which component would be greater? So in other words, flatter, right? So then the horizontal would be greater. So you can tell by the angle that the magnitude of the vertical component is going to be greater. So can you use your functions, your trigonometric functions, to determine the vertical as well as the horizontal component? So if this is theta, we already have theta, 60 degrees. What would the vertical side of the triangle represent? That would be opposite, right? Okay, so what would the horizontal component of that force represent then? That would be what side of the triangle? It would be adjacent. So you're looking at the sine function and the cosine function. So, a step further, okay, what does an equal sign that is kind of made of wavy lines, what does that mean? Approximately. Yes, very good. So that's exactly what that means. Okay, so this is the force of the athlete acting on the shot. So we can figure out that that's equal to approximately 87 newtons. So how do we do that? Okay, so we can use our sine function. And what's our angle again?
60.
Yeah, 60 degrees is equal to, what's the ratio? Yeah, opposite. And that's what we're looking for, right? In other words, this is the vertical component divided by what? What's the other part of that ratio? Hypotenuse. Okay, so then you just use your algebra, rearrange it. So sine of 60 degrees multiplied by 100 newtons. So you should come up with 86 point something, close to 87. Is everybody pretty well coming up with that? So it's approximately 87 newtons, a little less. Okay, so then teach me how to do the horizontal component then.
Does it matter which way? You want us to use cosine or?
I think, yeah, adjacent, right? So cosine 60 degrees equals, okay, so you got your adjacent side divided by your hypotenuse. Okay, so then if we solve that the same way, your horizontal component is what? It's about 50, right? Okay. Going back. All right, so we have a vertical force on the shot from the athlete. We have a horizontal force on the shot from the athlete. We have the force of gravity. Okay, is that a vertical or horizontal? Vertical. Okay, so is it negative or positive? Negative. Okay, so to figure out the resultant, which is going to be equal to about 68, we have to make another triangle, right? Because we've got how much vertical force from the athlete? About 87. And how much vertical force from gravity? 39. Okay. Let's just make it simple. Let's round up and make it 40. How's that? Okay. So what's our net vertical force? What's our net vertical force? Oh, maybe I can't write on it, but what's our net vertical force? What's 87 minus 40?
47.
Okay. So this is the force from the athlete. Okay, so we have positive 87 and we have positive 50. So we have positive 87 from the athlete, we have approximately negative 40. Wouldn't you rather use negative 40 than 39 point? Yeah, so we'll just do that in this case. So if we have positive 87 from the athlete and we have negative 40 from gravity, what's our net vertical force acting on the shot? 47. Yeah, positive 47. Do we have any other horizontal forces acting on the shot other than just from the athlete? So not unless Bryn is throwing into a hurricane. Okay. So really all we have is just positive 50. Okay. So what's that theorem we can use to solve for our resultant? Pythagorean, right? So can you run through that, see if you can get, what was it, 68? Something like that. I think it was. So we also also want to know the angle. Can you compute the angle of that overall resultant force? So you know all three sides, so you can use, I would encourage you just to demonstrate, you can use any of those functions if you know all three sides, and you'll get the exact same angle for your result. So what angle did you get? What did you come up with? You can use your inverse tangent function would be 47 divided by 68. Or no, that would be sine. Inverse sine function would be opposite over hypotenuse. So the inverse sine function would be 47 divided by 68. Cosine would be 50 divided by 68. Tangent would be opposite over adjacent, 47 divided by 50. What was your result for your angle? Yeah, so 40 theta would be equal to 43.
So that answer to that actual, like, what is the net force would be the second hypotenuse you think? For the 60?
This would be your answer. So what these are is just one part. So the force from the athlete. But you also have to consider that there's also gravity acting on the shot as well. So this would be your overall answer right here.
The whole track.
Yes. Yeah. So we have to consider both. So we started independently from the athlete and also from gravity, and then we put them together in this analysis. So this would be the overall when considering everything together. Haley, you have a question? Okay. How's everybody doing? Let me check in. Everybody doing okay? Shay, do you have any questions?
I think so. What did you guys get again? I'm making sure.
Okay, so,
Oh, 43.
yeah, over here in red, so this is from the athlete. But we also have to consider that gravity is also acting on the shot. So we put those two together, and this is our analysis over here. So 68 newtons and then 43 degrees there would be our overall answer. Everybody good so far? Ashley, do you have any questions?
No, not
Okay. Okay. So let's take a look at this one. So the vertical ground reaction force, okay, so that's the vertical component here, acting under a runner's foot is 2,000 newtons. Okay, well the frictional force acting forward is 600 newtons. So can you quickly compute what the resultant force would be? And I guess from a practical standpoint, my question is, what would this running form look like? And is it good running form? Go ahead and compute that at hypotenuse first. So can you see how we just move this arrow up here to make that triangle for the resultant? So you have a 600 Newton frictional force pushing forward and a 2,000 Newton ground reaction force pushing up. So a runner's foot is pushing down and back, and the ground reaction force is up and forward, right? And so you have two components. What we're looking for is the overall resultant. So you have your horizontal and vertical, and then you'll use the Pythagorean theorem to solve for the resultant. So one thing to know is the hypotenuse will always be greater than either of the other two sides, always. So because we have a pretty big vertical component, the hypotenuse is going to be over 2,000. So this is your angle theta right here. Okay, so 2,000 would be the opposite side. 600 would be the adjacent side. So what'd you get? 2,000. What was your hypotenuse or resultant? 2,088 newtons. What was your angle? So it's a pretty steep angle. What was the angle of your resultant? So because you have all three of those sides, you can use any of your functions to get the angle. So it's a pretty steep angle. Brian, did you get the angle?
No, I got 73 degrees.
Okay, yeah, that is correct. Should have 73 degrees. So it doesn't matter, but which one did you use, Brian?
I did sine.
Sine, okay. So sine would be 2,000 divided by 2,088. So opposite divided by hypotenuse multiplied by the sine of your, you'd have the multiplied by the inverse sine function to get that angle of 73 degrees. But you could use any of them and you'd get the same answer. Okay, everybody good so far? Looking at it from different ways, coming up with the resultant? Okay, all right. Couple more to go. Okay. All right, so let's take this discussion from outside the body to inside the body. Okay, so you have muscles. Muscles attach to bones through tendons. And so those tendons pull at different angles relative to their attachment point. So the biceps is used a lot because it's a superficial muscle that is easy to apply examples to. So when a tendon pulls on its attachment point, we call that the angle of pull. The angle of pull. So with the elbow more extended, you can see in this case, it's not completely extended, but mostly extended. We're talking about the angle between the tendon and its attachment point towards the elbow joint. So it's on this side that we're talking about, the angle of the biceps tendon and its attachment point on the radial tuberosity. So we're not talking about the away side, which obviously would be greater than 90 degrees. We're talking about the other side, the interior side. So does that make sense to everybody? Less than 90 degrees. So we're talking about the angle towards the elbow joint on that side of the tendon. Okay, so any questions on that to start with? Okay.
I don't think so.
Question? Okay.
We'll see if it comes up.
All right, so with the elbow more in extension, we have the overall force from the biceps. Okay, so that's your resultant. How much force the biceps is applying to its attachment point. Now, when the elbow is fully extended, that resultant force is going to have one or two components. So the first component is the rotary component. So that component acts perpendicular to the attachment site. That's the rotary component. The other component of this force is directed into the joint itself. So that component pushes the humerus, specifically the trochlea, pushes the radius and the trochlea together. So it's a compressive force, it's a stabilizing component. So at this point, with the elbows more extended, this resultant force has two parts. It has a rotary part. The rotary part is what actually flexes the elbow joint, and a stabilizing part. So that part does just what it says. It stabilizes the elbow joint. Okay. So we're diving into this, into the mechanics of muscle. The whole bicep force doesn't necessarily flex the elbow joint. So when the elbow is more extended, we have some of that force that is directed into the joint. That has no effect on flexing the joint at all. And we have another component that is actually rotating, flexing the elbow joint. So what I'm asking you here is, if the resultant is 800 newtons, that's what this is right here. That's our hypotenuse, right? The resultant. What is the stabilizing component? In other words, what's the component that's pushing the joint surface together? And what is the rotary component? That's the part that's actually flexing the elbow joint. So we can solve for this just like we've done with other problems. So theta is given to you already, so that's 30 degrees. So you're just taking the hypotenuse and the angle, and you're solving for the other two sides. So let's set this up. Give you a little history lesson here. Anybody know who this is? Larry Scott from Pocatello, Idaho, Mr. Olympia, 1965 and 66. He won the first two Mr. Olympia competitions. Died in Salt Lake City about 10 years ago. So, history lesson. This movement that he's performing here came to be known as Scott curls. Scott curls because that was his signature move that he went to train his biceps. So, what I've done here is copied a free body diagram from your textbook. So what I'm attempting to do is show you on Larry Scott, and then also where these force components are. So let me overlay some lines here. Okay, so there's your resultant force right there. That's 800 newtons. Okay, so you have two parts. You have a rotary part, and that part's actually going to swing the weight out. That's the part that flexes the elbow joint. That's the part that lifts the weight. You also have a stabilizing part. So that pushes the bones together. So the angle that we're talking about, the angle of pull, when the elbow's extended less than 90 degrees, it's this angle right here. So we can make a right triangle out of that. All I'm going to do is take the rotary part, and to make a triangle, what do I need to do with it? To solve for this problem, all I have to do is just move it up here, right? So then I've got my triangle. Okay, so I've got 30 degrees right here. So the rotary part that I moved up here is where opposite, it's opposite, right? So I gave it away to you. So the rotary part is going to be opposite, because all I did was move it up here. The stabilizing part is going to be the adjacent. So the stabilizing part is this. The rotary component is this right here. So 30 degrees opposite and adjacent sides with your 800 Newton hypotenuse.
Does it matter what component you move?
The only reason I moved it is to just make a triangle like what you see up here.
Right. But because you move that, then that makes that opposite. If you move
It's
the
the-
stabilizer, it would be opposite.
The other way, I think it's easiest just to move the rotary this way, but you could do it the other way. Yeah, you could move the stabilizing part and get the same answer. Okay, so what trigonometric function are we going to use to solve for the stabilizing? If it's adjacent and we know the hypotenuse. Cosine, so cosine of 30 multiplied by 800, because 800 is your hypotenuse, right? If this is confusing to you, just look over here. Okay, so you have 30 You have 800, you have a rotary part, and you have a stabilizing part. Okay, so if we're solving for the opposite side, we're going to use the sine part, right? So sine of 30 multiplied by 800 is what? What component would be rotary? Because this is the opposite side. So sine of 30 equals opposite over hypotenuse. So sine of 30 times 800 is equal to what? Okay, good. Good. Yeah, so the rotary part is 400 newtons. Okay, what about the stabilizing part? That's the adjacent side, right? So I could say cosine of 30 is equal to the adjacent side divided by what? Divided by your hypotenuse, right? So cosine of 30 times 800 would give you your stabilizing component or adjacent side. What'd you get? 6 something?
692.
Yeah, 692 newtons. So in other words, when the elbow is extended, more of that bicep force is acting to stabilize the joint versus do what? To flex the elbow joint. So, question, does that scenario change? Yeah, it does. So, another one of my favorite 60s, 70s era bodybuilders. Okay? So, when our angle of pull is 90 degrees, equal to 90 degrees, we have 100% rotary. 100% rotary. So, key point, the higher the rotary component, based on the angle of pull, the greater the expression of joint torque and strength. So if we were to take measurements of elbow flexor torque at different angles, from full extension all the way to full flexion, where would we find expression of the greatest torque, do you think? Right here. The reason is we have 100% of a rotary component. We don't have any forces that are acting to stabilize or destabilize the joint. It's all directed perpendicular or at 90 degrees to that attachment point. So wouldn't it be great if someone invented a line of resistance training equipment that fit the natural strength curve of our muscles? Someone already did. Okay, who's heard of Nautilus? Nautilus, the first line of resistance training machines from back in the 70s. Arthur Jones. It was kind of a nice concept, kind of a nice idea, because he was the first one to really look at matching the resistance to our normal strength curve. And then studies subsequently found that free weights you get just as good, if not better, results. So that's a little history. Okay, so we're all the way up, top of the range of motion. What have we got? We still have a resultant. We've got a rotary component. And at this point, we actually have what's called a dislocating component. So if you look up here, the angle of pull is greater than 90. That's on this side. And right here, this isn't the best picture, but if you look up here, greater than 90 degrees on this side. Our joint doesn't actually dislocate, it's just called that. But rather than pushing the joint surfaces together, this force tends to pull the joint surfaces apart. So even though we've got that olecranon and olecranon fossa back there that prevent, you rarely see the elbow joint dislocate, but that's the direction of forces away from the joint there. So the whole take-home message is that at full extension and at full flexion, we have less of a rotary component versus when we're right at a 90-degree angle of pull. So that's the mechanical take-home message. Okay, so right at the end of the chapter, I appreciate everybody hanging in there. This is the very last problem. Very last one of the days. How many of you flipping television channels have ever seen these monstrous humans pulling trucks? Okay, so we're going to analyze this. Brian Shaw, I don't know how many times he's won the world's strongest man, a few times. A 200-kilogram strongman competitor, so these are big men, over 400 pounds, is competing in the truck pull event. He pulls forward and slightly upward on the rope, which is attached to the truck. So this is the rope that he's pulling on, and this rope on the other end that you can't see is attached to a truck. With a force of 2,200 newtons acting at an angle of 14 degrees below horizontal. Brian also pulls on a rope with a horizontal force of 650 newtons. So he pulls on this rope. What does the rope do? Pulls back, right? Reactive force from the rope is 650 newtons. What is the overall reactive force from the ground against Brian's feet just prior to initiating movement of the truck? Okay, so if you could have this pulled up somehow, either on your phone or laptop, and then I'm going to go clear our screen so we have plenty of room to work. Probably the first thing that would be good, if you know someone's mass, eventually you're going to have to use their weight. So calculating weight in newtons from 200 kilograms would probably be a good first step. So we're just going to get a new screen. Okay. So here's our free body diagram. So if you look right at the end of chapter 1, we're going to go through these steps. Okay, so we have lots of forces. So we have mass of 200 kilograms multiplied by negative 9.81 meters per second squared. You should have calculated 1,962. Did everybody get that? So is that negative or positive? Negative, because it's weight. Okay. So we have two different forces acting through his feet. So he's pushing down and back against the ground. What does the ground do? He pushes down and back. The ground pushes up and forward. So this is the reactive force from the ground. F of S, what do you think that stands for? Capital F probably stands for what? What's the force between the feet and the ground? Friction. Yeah, friction. The S probably stands for what? Static friction. So if you read the problem, it's just before he initiates movement. So static friction. So he's not moving yet, it's just before things start to roll. Okay, so this is the vertical reactive force from the ground. So we're going to first of all divide this problem into parts. So we're going to go with parts that are horizontal, we're going to go with parts that are vertical. So let's go ahead and we'll just start listing what we know. So we know that there was a positive force for friction, right? In newtons. We don't know what that is yet, but we're going to solve for it. Okay, vertically, we got the vertical normal contact force from the ground, so we also don't know what that is, but we're going to solve for it. So you told me that weight was equal to what? 1,000.
962.
Okay, so we can put that over here. Okay, so that's a vertical force, right? So we're going to put it right where in that category. So minus 1,962. Okay, so what other force do we have? Have the force from how much was the resultant force from the truck? He pulls on the truck. What does the truck do? The reactive force from the truck was, what was the?
2,200.
Okay, so what was the angle?
14 degrees.
Forgive my poor artwork. 14 degrees, right?
Yep.
Okay. So you have, this is our poorly drawn right angle. So this would be what? Be the hypotenuse, right? This over here would be what?
Opposite.
Yeah, opposite. So this would be the vertical or horizontal component of this resultant force. This would be the vertical, right? Would it be negative or positive? Is it going to be negative or positive? It's going to be negative, right? Okay, so this resultant force is acting 14 degrees below the horizontal. So we know part of that, a small part, is in the downward direction. An even bigger part is in the horizontal direction. What side would this be?
Adjacent.
Next to theta. Yeah. So this would be the vertical component. This would be the horizontal component. Okay. So we know that we're going to come up with something that's going to go right here. That's going to be negative. So how do I do that? Can you solve that for me? If we want to know what the opposite side is and we have the hypotenuse, what's the function we use? Yeah, sine of 14 equals the opposite divided by what? Hypotenuse. So sine of 14 times 2200 gives you your opposite side, which is what? Put that in, work it out. Sine of 14 multiplied by 2200, what do we get? Should be 532. Yeah. You see how it's the vertical part? This is an overall downward force, but it has a horizontal component and a vertical component. So this is so we're setting that equal to 0 because we're not moving yet. So the horizontal and vertical components are in equilibrium. Okay. All right, so what else have we got? We got this up here. What did you get for the adjacent part? Pretty big number because it's mostly horizontal. So if you want to solve for adjacent and you have the hypotenuse, it's probably maybe cosine, right? So cosine of 14 multiplied by 200. What'd you get?
2,135, if you round it.
Okay, 2,135
135.
newtons. There's reactive force pulling back in the opposite direction. Okay, one thing we missed. What about the reactive force from the rope on his hands? How much was that?
650.
Yeah. Okay. So positive 650 newtons equals 0. So why again are both of these equal to 0? Because we're not moving, we're in equilibrium. Okay, so we're really close. So can you solve for the force of static friction horizontally? Can you just take all that, come up with one number, rearrange that? $1,000.
485.
Yeah. Positive, right? Because what happens to this number when you move it to the other side? Yeah. Just high school math. So 1,485 newtons. What'd you get for your vertical component? Should be another positive number, right? Pretty big number, 2,000.
194.
Mm-hmm. Okay. So we are super close. Make another triangle. So you have two parts. Okay, so let me stop right here. How many understand how we got the overall horizontal and overall horizontal vertical? Do you have any questions? So it's just breaking something down, looking at the situation, coming up with an overall number. And then you put everything together right at the end. So you build that last triangle right at the end and come up with the overall value. Okay, so let me just go back. You can see. So you have Ry and you have R f of s. Okay, so what we can do is we can make a triangle out of that. Can I, if I save that, can I put up a blank board? Is that okay? And I'll post these if you want to refer to it later. Okay, so we have 1,485 newtons. We have, and this won't be drawn to scale obviously, how much vertical? 2,494 newtons. Okay. So this is our resultant. This is our angle. Okay. This Pythagorean theorem. And you gotta come up with your angle, use the inverse function for that. Got a result so far? Anybody? It's gonna be greater than either of the two sides. 2902. Good. That's correct. Then you can use any combination of your sides to solve for the angle. It's a pretty high angle because you have a lot more vertical than you do horizontal, so it's probably going to be close to 60, give or take. What'd you get?
About 59.
Okay, that sounds good. Everybody agree? About 59 degrees. Okay. All right. That's a lot of trig. Have any questions?
So just the meaning of the 2903 is just the overall force.
That's the overall. So we put everything together, and what do we get? That's what we have right there.
And the angle is important?
Yep, that's the angle into the ground. That's going to determine, it looks like to start with, he's going more up than he is out. So I don't know if that's a strategy that they use or what, if they initially start up to get the truck moving or what. That's what we got. Okay, so that's chapter 1. Chapter 2, got some fun stuff coming up with displacement, distance, velocity, speed, and acceleration, as well as projectile motion. So I'll see you on Wednesday. Thank you. Why don't you just keep your sheets? It's a good study tool because problems on the exam will be very similar. So, thank you.
On the study side, is there going to be like actual practice problems or just
That's kind of what all of this is. But it'll be very similar on the exam.
How do you know if you're supposed to be
You'll have to,
Yeah,
you'll be
are
well
you sure?
prepared.
Are you supposed to know that? When to do it? Yeah, if you use like regular sign and English, or the inverse, you use the right. I get me. You need to write that down. Yeah. So simple. You use the regular